example of free fall of elastic suspended table. As I said the last times, yeah, it's depend on you, yeah, where to choose the zero level. It's up to you, but the best one, yeah, and the best choice, let's say, is to choose where we know the initial condition, okay, not the actual or arbitrary position, let's say, okay. Why? Because in the initial conditions, we know everything regarding, let's say, the geometry as well as the, the motion at the initial position. It's always maximally, in general, it's always given. Yeah. Okay, we will continue now with the same example. Let's say then we take here, yeah, this particular case, depositing mass at rest, yeah, on an elastic foundation here, where we have at time t equal to 0, the high h is equal to 0, and initial speed v0 is equal to 0. At time t equal to t1 on an arbitrary, um, let's say, state, the maximal spring elongation, then v will be equal to 0. That it means v1, yeah, will be equal to 0, and the maximum we reach in this case the maximum spring force. Then now this are, let's say, equivalent. Yeah, this the one things here we have the contact force between the mass m and the ground, and here we have on the mass m we have the spring force. Okay, then this let's say mass or a problem is under gravitational acceleration g. Now if we take the zero level here, okay, it's equivalently to write it somewhere here, yeah. Then we have the kinetic energy T0, it's equal to 0 as the velocity V0 is equal to 0, okay. T0 that we said, it's only the half of the mass velocity square. This is the kinetic energy. Now coming as V0 is equal to 0, this is the initial kinetic energy. This is will be equal to 0. Now we take the, let's say, the potential energy P, 0, as well as the potential energy of the spring. Now P0 is equal to 0 as the 0 level is here. That is means there is no high. H is equal to 0. And we have also the potential energy of the spring. As we have here the potential energy P0 of the spring here, PF0. The spring is unstretched, that is means it has no elongation. In this case, it's equal to 0. Now, if we take the kinetic energy at time t1, okay, that it means as actual state or arbitrary state, we said that V will be equal to 0 and the maximum spring force, yeah, the spring force which will reach its maximum. In this case, P1, yeah, will be minus mg x max. If we cut here, that it means the spring, yeah, will elongate with x max, yeah. And if we take the zero level here, that it means here the mass m will cover this elongation, let's say x max, and will be in negative as the zero level is somewhere here. That it means we are in negative x, then we have minus mg multiplied by x max. Now we take the potential of the spring force here, then we get here the half of c x max square. Okay, we know that the potential is only the force multiplied by the displacement, yeah, on the same direction as the force. Now we have the conservation energy. The conservation energy is only the initial kinetic energy plus the potential energy, the initial one at time t equal to 0, will be equal to the kinetic energy at time t1 plus the potential energy at time t1. Okay, then it means at time t1 we take the sum of this three parts, and at time t0 we take here the sum of the t0 plus p0 plus pf0. Then if we do so, then we can get here the maximum elongation of the spring will be given here by 2 times mg divided by c. As you can see here, if we take x max, yeah, out of the integral, we see that x max is either equal to 0, and this is correspond to the initial state, that is mean unstretched spring, and or it will be equal to mg divided by c plus these terms, and we will give here 2 times mg multiplied by c, which is here c, the coefficient, spring coefficient. The maximum force, spring force, is clear here. The force F max will be equal to 2 times mg, as we know that F max is only c multiplied by x max. Okay. Now, if we take the derivation of the equation of motion with conservation of energy, then we have the conservation of energy integration of the forces along the path curve. That means in the same direction as the path. This will permit the differentiation of the work to establish the equation of motion. Now, if we take the vertical throw, equivalently the free fall, the potential energy for arbitrary position Z will be here P at any, let's say, path or position will be mg multiplied by Z. Okay, the kinetic energy is the half of the mass multiplied by the velocity, as the position is given by Z, yeah, is the height at any time. Then we have the velocity of the position the time derivative of the position z will be the velocity here, z dot. Then if we write that the conservation energy will be constant, that it means the initial um, energy will be equal to the actual energy. If we make the sum here, okay, of the potential energy plus the kinetic energy will be constant, then we make the time derivative. The time derivation will be here of the first term mgz, at z is time dependent, okay, at any, as I said, arbitrary state. In this case, we have mg multiplied by z dot, okay, plus the time derivation of the kinetic energy here will be 2 times m z dot z dot dot, okay, as we know that dz dot over dt will be only the acceleration. And the constant here, its time derivation is equal to 0. Then we get here mg plus mz dot, z dot will be equal to 0. Then for arbitrary velocity, this is valid only if mg, that is means the first terms will be equal to 0, as dot cannot be equal to 0. Okay, that is means we have two possibilities here, either z dot will be equal to 0 or the first terms will be equal to 0. The z dot cannot be equal to 0. If it's 0, that it means, yeah, either that it means there is no velocity, then it means there is no motion. This case will be rejected, okay? Then it means we have only the first terms will be equal to 0. Then we get here minus mg will be equal to mz dot dot, yeah. Then it means if you look here, z dot dot will be equal only to minus g. And this is analog result as with Newton's second law that we have seen, yeah, in the beginning of the third part. We take the case, for example, of the pendulum, where we have seen already this with Newton, the method of Newton law and D'Alembert. Then we take here this mathematical pendulum with an arbitrary angle here, phi, okay. The pendulum, the rod has the length L, okay, and which moves with certain initial velocity v0, okay. We apply initial velocity v0, and we have at time t1, we have the velocity, let's say v, or you can call it noted by v1, okay. Now we said that we take the 0 level, it's the choice, yeah, it's depend on your choice, and as I said, it's better either, yeah, to make the choice that where we know the initial state, yeah. At the initial state, we know that phi will be equal to 0, okay, and also we know the height, which is the length here, L, okay, and we know the initial velocity v0. Yeah, this is we make here the 0 level at this position here. Now, if we look to the potential and the kinetic energy, if we look to the first byte, let's say P, okay, at this position here, the potential energy, what we have here, we have the length L, okay. Now, if we take the force applied on the mass M here, will be only mg, it's the weight, okay. Mg is given in this direction here, the vertical direction, that is means is the same direction as g, yeah. And if we take now the distance to the zero level, yeah, let's say the cover distance, is only L multiplied by 1 minus cosine phi, okay. This is here, this part here, it's only L cosine phi. That is means this part is only L minus L cosine phi. This is now the cover distance, yeah, of the mass or the particle here, M, yeah, to zero level. Now, if we take the energy, it's only the half of the kinetic energy is only the half of the mass multiplied by the velocity square. And the velocity square, we have already seen, it's only L phi dot. Okay, this is, we have seen it several times, yeah, and in different example with D'Alembert, also in kinematics of um, the particle. Now, if we make the conservation of the energy, that is means we can take that the actual or the arbitrary energy, which is decomposed into the potential plus the kinetic energy, will be constant. Okay, constant, that is means also will be equal to the initial energy. Now the derivation of here, we have cosine phi, okay. We have also phi dot here. Then if we make the time derivation, then we have here d over dt of cosine phi. This is as as cosine is depending on phi, yeah. Then we apply what we call the chain rule. That it means we derive, yeah, with respect to phi, and then phi with respect to the time t, okay. Then we have here d cosine phi over d phi multiplied by d phi over dt. Yeah, the derivation of the first terms will give only minus sine phi, and the second term will be only phi dot. Then, if we take now this term here to derive it, then we have d over dt phi dot square. The same principle. Here we have phi dot. That is means we can make d phi dot square over d phi dot, and not d phi, multiplied by d phi dot over dt. Here, is the acceleration, phi dot dot, and here it's 2 times phi dot, okay, with respect to the variable phi dot. To apply to conservation energy, we have here now only we are placed in this term here, okay. Now we have mgl sine phi dot, yeah. We have here the derivation of cosine phi multiplied by phi dot plus the half of the mass multiplied by L square and 2 times phi dot equal to 0. Then we keep here phi dot, yeah, as here out of the term. Then we have either the first term will be equal to 0 or the second term will be equal to 0. The same as the previous example. Phi dot, when we phi dot is equal to 0, that is means it's at rest. This second case, yeah, will be rejected. That it means we have only the first term should be equal to 0. Then we say for an arbitrary velocity, this is valid only if the first term will be equal to 0. That is means this term should be equal to 0. Then we have the following relation, and therefore we get, yeah, the differential equation, yeah, phi dot dot plus g divided by L sine phi equal to 0. And this is the same result as with Newton's second law or D'Alembert principle. Yeah, you can look to the same example using Newton and D'Alembert. We found, yeah, the same result. Okay, now I have finished with the part 3. Okay, now we look to the um, kinetic or the conservation of energy, yeah, with, let's say, yeah, applied for the rigid body. Okay, I will shift to part 4. Then we had the general equation of motion, yeah, when we have for the mass point or the particle, we got from the Newton's law, we had to apply the force law or the equilibrium. The same principle with D'Alembert. Okay. This is for the rigid body, in principle analogous procedure that we use the same things. The difference is only the kinematic equation. Yeah. Yeah, for the rigid body, of course, we have not only the translation, yeah, as for the mass point, we have also the rotation. Then it means additionally we have compared to the particle, okay, we have additionally the law of moment for rotation part of motion. Yeah, let's say for the particle, the rotation, yeah, is neglected. Yeah, why? Because we have one point. Okay. Then we say the kinetic energy or the kinetic of rigid bodies was developed by Euler. Yeah. The kinetic of rigid body treats the relationship between the external forces acting on body and the corresponding translation and the rotational motion of the body. Now we take here the planar kinetics of a rigid body. Yeah. Then we have this rigid body and we take an arbitrary point or let's say mass. We call it by, we note it by dm. Okay. Then we have the point A on this body and the dm here, we note it by the point P. Okay. Then what we have here, we have the forces which are infinitesimal forces which are here applied on this mass, the m infinitesimal mass. What we have here, we have the coordinate system x, y, okay? We take for the point A the vector position R A, which has the component in x direction xa and the component y a in y direction. Now, as you know, if we want to get the acceleration or the velocity of this point here, P, okay, we know that the general relation is Vp, it's only Va. P. Okay, it seems that there was problem with the connection. I will continue. Now, as we said, we take the Cartesian coordinate system xy, arbitrary body point here, A. The component of the vector A, P, okay, we note it by xi and neta, okay, xi in x direction, neta in y direction. Xi can be decomposed here, can be represented or given by r cosine phi. Okay, that's what we have here. We have C as we have the position R between A and P. This is we noted by R vector. This is the distance between the point A and the point P. We have Xi here, yeah, R cosine phi, and the neta, it's R sine phi. Then the body, the point here, rotate, okay? When it's rotate relative to A or to coordinate system X, Y, yeah, this is denoted by omega. Omega will be only phi dot here, yeah, this is the angular velocity. A and P rotate around each other with omega, okay? Now, if we take the position of P, yeah, um, let's say at with respect to this coordinate system x, y, what we have here, the position P to this point O, yeah, we have xa plus xc, okay? Then we have here xa plus r cosine phi. Double derivation with respect to times. This, if we derive now, x, yeah, given by this expression here, we will get x dot a minus r multiplied by phi dot, as cosine phi is dependent on phi, yeah, and phi is the phi dot sine phi. Now we take the acceleration in x direction, then we have x dot dot will be the first terms x dot dot a minus the same term here, chain rule, okay? R, we take it, yeah, as, yeah, we keep the same distance between P and A. And now what we have, phi dot and sine phi. Then we derive the first term here, phi dot, and then we derive with respect to time of sine phi. Then we have here phi dot sine phi. This is for the first term phi dot, plus here the chain rule. Okay, we will get here the derivation with respect to time of sine phi will be only phi dot cosine phi. X dot a, the first term, here the second term. Okay, as you can see here, neta is r sine phi. Yeah, if we replace it, we get here minus n neta phi dot. And we have the third term, which is only minus xi phi dot square. In y, okay, you can hear me. Then we have here y dot, y of the position of P in y direction. Then we use the same principle as for the x coordinates. Yeah. Then we have here the simple and double derivation with respect to time. Well, give for P the same principle, y dot, the velocity, and then the acceleration. Then, yeah, if we take now the polar coordinate system represented by the unit vector or basis vector r and phi, what we have here in r direction, we have r phi dot square. Yeah, this is the acceleration. Let's say the normal acceleration. R phi dot. This is only the circumferential acceleration. Yeah, remember we said in phi direction, yeah, the acceleration is only on. Okay, it seems that there is a problem with the connections. Yeah, sometimes it's come and sometimes, yeah, not, but it's only short moment. Yeah, we'll continue. Okay, now what we do? We make the projection, of the acceleration in circumferential direction, yeah, on x direction and the y direction. The same we projected on x direction and the y direction. Okay. Now we have here, we said that acceleration component due to rotation of P about the reference point A. Okay. We said that the tangential, as we said, differential are phi dot dot along phi direction, and we have the radial one or the normal one, yeah, along the radial direction, AR. Now we take here infinitesimal volume element dV with mass dm in point P. We take this dm, yeah, with infinitesimal mass, yeah, and then we can, after this, integrate to get the whole body, yeah. Now the m, of course, has the velocity, the volume. On acting forces on the m, yeah, there is the internal forces. We note it by AI, dFi, okay. Example forces due to normal and shear stresses, and there is the external forces which are applied on, yeah, the noted by dFa. Now, if we take the second Newton law, yeah, for the m, what we have to get the equilibrium with the sum of the forces equal to the mass multiplied by the acceleration. This is the principle of the second Newton law. The force first part, which is the A, yeah, the external forces along x direction, we apply the same principle in y direction, and we have the internal one, the f I x, and the same, yeah, which is the mass multiplied by the acceleration. Here, for this infinitesimal mass, we have the acceleration in x direction, x dot dot, and the acceleration in y direction is y dot dot. Okay, we have seen that x dot dot, return back. Here, x dot dot is given by the following relation. Yeah, the same principle for y dot dot is given by the following relation here. Then we replace, yeah, here by x dot dot by its expression here. The same for y and the acceleration in y direction. Now, if we make the integration of all forces acting on the mass element dm, that's to generalize this. Then we have here the generalization to the whole body. Then we have the integral, yeah, with respect to dm. We have now external one in X direction, and the same principle in Y direction. The internal forces, yeah, will be equal to zero. Yeah. Why? Because each dFi causes an equal and opposite reaction force. Okay. At time t1, we have txy. This is the tangential one, okay? Or let's say shear stress or shear force. And this is the normal one, okay? We note it by sigma. At time t1, t2, we have, of course, yeah, let's say at time t2, we make plus dt. Okay, this is the actual time or the arbitrary time. That it means this will cause, okay, d sigma x, yeah, as its cause, yeah, this is in normal direction and also in shear direction or shear stress. We have here d, okay. Now, if we make the sum, we have here, yeah, sigma xy, it's outward, and this is inward. Now, if we make the sum of the two, yeah, this will give zero, and you have only d tau xy, and uh, and d sigma y. Then you have here sigma y, you have sigma y opposite direction, then you will get here d sigma y will be equal to zero. Now, if we make the integration of all external forces, okay, then we have in xy, in x direction, we integrate, yeah, um, over the whole mass or the whole volume. Then we get the first term here, okay, x dot dot a dn. This is the first term here, minus phi dot dot. This is kinematic neta. It's geometrical one. Yeah, dm. Yeah, if the volume, it's only dm. Yeah, multiplied by the uh, the position here. Now this is a kinematical one. Neta term, the same for xi. Yeah. Then if we develop here, well, we have three terms here. Okay, the same principle for the force in y direction. Now the integral of dm, yeah, infinitesimal mass, yeah. If we integrate for the whole body, we will get the mass m, yeah, which is the total mass. Then we obtain now, yeah, the force law. This is will be here now. This term, yeah, when we integrate here the m, we will get here the mass. Then it means we get here the force now is the mass multiplied by the acceleration of the point A, yeah, plus these two terms here, yeah. The same principle is used here for in y direction. Now, if we use this, the same principle with the D'Alembert inertia force. Okay, we introduce showed here by the red color. We get here x dot dot dm and y dot dot dm. Yeah. Then we say here in dynamic equilibrium for the mass dm here, in addition to the equilibrium equation of forces, an additional equation is needed to specify the state of rotation about any arbitrary reference point E. Yeah, and this will be the equilibrium equation of moments. Then we have here C, okay, multiplied by the sum of the forces, the external and internal, in x and y direction. Additionally, we have these two terms here, and this is due to this one. Okay. External forces. Okay. If we make here C the F Y E minus neta the F X E. This is the external forces noted or indicated by the letter A. Yeah. The internal one indicated by the letter I here. Okay. Now, if we make this, will be equivalent to the external moment here. We note it by M A A. Okay, at the point A, yeah, and A indicate the other symbol here. A, it indicates its external one. Now, if we integration of the moment due to the internal forces, we indicate the same principle. We do I here, yeah, and this will be equal to 0. Then this result will bring to the following, yeah, relationship here, MA. We have here X the F Y A minus neta the F X A. And if we make here the time derivation, or let's say, then we get here X Y dot cy dot minus neta x dot dm. X dot and y dot are given in the expression are given in the previous slide. We substitute, okay, we get the following relation where we have using Pythagoras, we have c square plus neta square. It's only the distance between the point A and the point P square. Now we get here the law of moment. Now the force law and the law of moment have been formulated for an arbitrarily co-moving reference point A. Both force law and law of moment can be simplified in one. Why? Consider the central weight of the body. Yeah. In this case, here we note it by S. This is the central weight of the body, or center of mass, let's say. accelerated point, yeah, a special case, the contact point of rolling wheel. We take this 3 as a reference point, yeah. This will be illustrated in the following now. Now we take the center weight as a reference point, S here, okay? We have our point P. Now, instead to use the point A, we will use the center weight S. Here we note it by here the distance to the center weight is Xi, as we have seen, and neta. Okay. Now we take what we call static moment of area about S. Okay. This is, you should have seen it in mechanics 2. Yeah. This by definition is given as the integral with respect to the mass m, Xi dm. This is in x direction and neta dm in y direction. The force law now, yeah, we take the force law at the center weight here, S. And this is we noted by the mass multiplied by the acceleration in x direction at this point S here. The same for y direction, the mass multiplied by y direction, yeah, at point S. Now the law of moment about S, it's ms, yeah, it's v dot dot, the integral of r squared dm, and this is, we note it by is v dot dot, okay? Is, this is the important part, yeah. This is the mass moment of inertia, yeah. We call it, yeah, is known as the mass moment of inertia, okay? And we have always this relationship. It's the moment of the center weight, yeah. It's always the mass moment of inertia multiplied by the angular acceleration, okay? And this is we wrote it by definition here. Is it's only the integral with respect to the mass m r square dm. Okay, r it's only here the distance between s and p. Okay. Now, the principle of motion of center of mass is the Newton law for the associated mass of the body. The equation of motion for the translation of the center of mass and the law of moment give the equation of motion for the rotation about S. Yeah. Now we get here the full description of the planar motion of the body. Now, we take a non-accelerated point as a reference point, okay? Now we take here a support point A, okay? This is that it means, yeah, do not move, that whole body rotate, yeah, around this point A. Now we have here, as it's fixed, its acceleration in x direction and y direction are equal to 0. Yeah. Now, if we take the law of moment about A, we have this relation here. We have seen, return back, that the moment is always I, the mass moment of inertia. Yeah. I call it moment of inertia for simplification. multiplied by the acceleration or the angular acceleration. Yeah. Now, if we change to, for example, any point here, A, it will be apply the same equation. Yeah. And A will be A phi dot dot. Okay. Take another point, the same principle. What it change as the body has the same angular acceleration. Yeah, at any point you have the same angular acceleration. What it will change only the moment of inertia. Okay. Now, IA, the mass moment of inertia about n axis through A perpendicular to the plane. That is means here we have IA. It's always defined by r squared m. Now r, it's the distance between A and P. Okay, and still to get here what we have seen between S and P. Yeah, for the center weight. Now we take this simple example, the contact point of a rolling wheel as a reference point. That is means here we take this contact point M, yeah, and this we take here the infinitesimal mass, yeah, we note it also by P. We have our coordinate system, Cartesian coordinate system XY, okay, and this will rotate with the velocity, angular velocity phi dot and angular acceleration phi dot dot. We note that m, it's different from instantaneous center of acceleration. If you remember, okay, we said the contact between the two, here the wheel and the ground will be the center of um, uh, the instantaneous center of rotation and not, yeah, of acceleration. We have here x dot dot m, yeah, will be equal to 0, and due to symmetry we have here, if we take c here, okay, we have the left part, the right part will be, yeah, opposite to the left part. And this is when we integrate now the static, let's say, moment, this is will be equal to 0. Okay, then it means we have dm at the right part and we have dm at the left part. Okay, and the two are symmetric. Yeah, then it means that here are opposite sign. Okay, in C, and this will give 0. For MA now, the moment about A, yeah, the external and not internal, then we have the relation. We find this relationship. The law of moment for this case, M at the point M, yeah, the moment at the point M will be the same. We use the same equation, Im, this is the inertia moment, yeah, multiplied by the angular acceleration. The same principle, Im r squared dm. Now, in this case, r will be only m, yeah, the distance between the point M and the point P. This is, we said, Im is only the mass moment of inertia about an axis through M, the perpendicular to the plane. As we said here also, this terms will be is equal to 0. This is will be neglected. That it means here, yeah, will be equal only to the first term. Now we're coming to the important part. Yeah, we will see this is, as I said, it's only to show how to come, yeah, to the equation which will use in reality or to solve the problem. Yeah, the things it's of course when you are dealing with the rigid body, yeah, each body, yeah, has its own shape or geometry, and this is, yeah, we use for the moment the same equation, yeah, the inertia moment I multiplied by the angular acceleration. What it will change? It will change only the I. That it means it will change only the inertia moment. Yeah, and this is the moment of inertia, yeah, or inertia moment. Let's say this has, yeah, depending on the geometry, and this is we show how to get it, and we will see it in tutorial for each case. Yeah. Now, by definition, is this one. I S at center width, yeah, also at any point, it's only the integral with respect to the mass r square dm. Okay. In our case, for the center width, it's S, the distance between the point S and P. Yeah. Now we take the example of the circular ring. Okay. Circular ring, that it means we have the infinitesimal mass dm. This center weight is S here at the center of this circle. We have the whole mass here m, and this is geometrically can be represented by the radius r. If we take now the moment of inertia about S, if we take now the distance between the point, the infinitesimal dm to S, yeah, sp, this is will be only the radius r, yeah. Then we make the integral of r squared dm, and we have here r is constant, okay. Then we integrate only dm, and the integral of dm will be only m, okay. And now keep in mind that for the mass moment of inertia, the is will be only the mass multiplied by the radius square. Now we take the case of circular disc or cylindrical drum. Okay, the total mass will be m. Here we take the thickness will be t. Okay, now if we look to the m is defined, yeah, always by the density rho multiplied by dv. Yeah, the density depends on the material, yeah, that you are using, yeah, or it's considered for each materials, yeah, glass, let's say, steel, yeah, woods, and so on. Each one has its own density. Now, if we look to the rho, it's constant, which is depending on the material. Now we look to the the infinitesimal volume dV. Yeah. If we look here, dV will be defined only by R dphi dr multiplied by the thickness T for the cylindrical case. Yeah. Now we look here geometrically. Yeah, in geometry we have our point P. Yeah, we have our centroid S. We have our infinitesimal mass dm. Okay, here dm has with the angle phi. It's more easy to use the polar coordinate system, yeah, or the cylindrical coordinate system. We have here the distance r and r plus dr here. Then if we look now, the volume, it's only the surface multiplied by the thickness. Okay, the surface here, this part here, it's only the r multiplied by this part here, ds. And ds will be only r d phi. Okay, as it's very small, yeah, if we take the tangent of d phi, the tangent d phi will be only d phi. Now, if we look to the moment of inertia of both s, we used the same equation, by definition r squared dm, okay, and now we replace dm by rho dv, yeah, and dv is r d phi dr multiplied by the thickness t. If we replace here everything, that is means here we have now two variables, dr and d phi. R is varying from 0 to capital letter R, which is the radius, yeah, and phi will vary from 0 to 2 pi, yeah, that is means for the whole, now integrate for the whole disk or drum. Now, with respect to this, okay, the integration from 0 to R, we separate the variable, yeah, we take this part which depend on the radius, yeah, R, then we have R3 dr, and if we integrate, we get the fourth R4. Now we take the second one, yeah, which depend on d phi, and here we have d phi, the integral of d phi from 0 to 2 pi, then we get here 2 pi. If we replace everything here, what we get here, the mass of the disk, yeah, it's mass rho multiplied by v, okay, and now we get here the moment of inertia will be given at the center of it, yeah. It's very important where is the point, yeah, when you are looking for the moment of inertia. At the center of it, it's only the half of the mass multiplied by r square. Okay, this is, yeah, in, let's say, books, yeah, you will for each geometry, yeah, you will find the expression of moment of inertia. Okay, now we take the third, let's say, geometry. We take here the thin bar, yeah. Then we have the total mass, it's m of this bar here, and the length is L. Okay, we have constant cross section A here. Now, if we take this dm, okay, we have dm, it's only rho, the density, multiplied by dv, and dv is only the area here, or the cross section A multiplied by the infinitesimal distance in x direction, dx. Okay, now the moment of inertia about s, same equation. Now we have only to define r square, okay, and if we replace now here, r will be x square in our case. If we take the point P here to the center of it, the distance is only x, then we have x square, and the m is only rho a dx. Rho and a are constant, yeah. We take them out of the integral. That is means we integrate from minus L over 2, the half of L, to L over 2. Okay, now when we integrate here, we integrate x squared dx. Yeah, and the integration of x squared dx will be x cubic divided by 3. We replace, we get here is is only rho a L 3 divided by 2, 12. Sorry. Now, if we keep here the mass m here of the bar, it's rho v, of course, then rho a multiplied by L. Okay, we replace here a by its expression, then we get here is, it's m multiplied by L square divided by 12. Okay, this is for the thin bar. Okay, now we take the fourth geometry, which is the rectangular disk. Okay, the total mass is m, the length is a, and the width is b. The moment of inertia, the difference here, yeah, we have m multiplied by L square divided by 12. Okay, in our case here, for the rectangular disk or plate, it's the same mass divided by 12. The difference here is only, yeah, this length here, L. In our case, for this car, the case here will be m divided by 12, a square plus b square. Okay. For b greater than 0 is the particular case of the thin bar with a equal to L. Yeah. Then it means if we now neglect the width here, b will be equivalently to the thin bar. Now coming, this what we have seen, this expression or equations are always, yeah, about the center of it. Okay, that it means the expression geometry expression of the moment of inertia are given the for the fourth geometry what we have seen, all formulation are given about the center of it S. Okay, if we take now another point, yeah, this we use, yeah, what we call the Steiner law. That it means like we calculate I, or let's say moment of inertia, about S, and then we shift it to an arbitrary point. To shift this is we use what we call here the Steiner's law. Yeah, and this is you should have seen it for the inertia of moment in mechanics too. Yeah, when um, you calculate, for example, yeah, the let's say the for example for um, I profile, T profile, and so on. Yeah, in construction, for example, this is we use what we call the Steiner law. Yeah, in standard, all formulation of the moment of inertia are given at the central weight, and after this, if we want to calculate everything for any arbitrary point, in this case, we use what we call here the Steiner law. Yeah, and this is in mechanics we call them, yeah, um, Steiner law, or for mechanics too, the second moment of area. Yeah, as I said here, for the mechanic too, we use the second moment of area. Now, how we do this? Yeah, we take the same example or description as before. We take this fixed point E with um, zero acceleration. Yeah, we have here the distance between P and E. This is represented by the vector R, and we have the distance between E and the center width. We note it by RS, and the center width to P by delta R. Yeah, that it means R, it's only RS plus delta R. Okay, now if we take delta R, we decompose it into two components in X direction and Y direction. In X direction, we note it by delta Xi, and in Y direction by delta neta. Now, if we look the relationship between the mass moment of inertia about center of mass point S and point E. Now, what we have seen the uh, inertia, moment of inertia is given about S. If we want to calculate it about E or about P, in this case, we use what we call the Steiner. Now, the mass of moment of inertia, according to what we have seen before, IA, this is the distance between the point A and P, square dm. This is, yeah, by definition. We have seen for different geometry at the center weight, okay, we had IS, okay, is the distance between S, the center weight, and the point P square dm. Yeah, that is means one have here IA is only R square dm. That is means we have here R square dm, and for here S we have delta R square dm. Yeah. Now, transformation for R, C, and neta in X and Y direction. Yeah, we have R square. It's only C square plus neta square. For at the center weight here, we have R S square, which is equal to C S square plus neta S square. delta R, yeah, the same principle. Now what we look here, Xi here, okay, it's only here, as you can see it's Xs plus delta Xi, yeah, from the point A to the point P, yeah. Then we make the sum, the same in y direction. Now if we take R square, we replace Xi by its expression here, and the neta by its expression here. Okay, then we develop, then we get the following relation here. Yeah, Rs square plus delta R square plus 2 times, yeah, the product, yeah, between the Xi here and neta. Then we get here the following relation for the moment of inertia about an arbitrary axis through A. Now we have IA, it's R squared dm by definition. Now we take term by term, yeah, here. Here, if we take this delta R square, the integral of delta R square dm, delta R, if you can, we have seen it, yeah, for the integral of delta R square dm, it's only the moment of inertia, yeah, about point S or about point here, about the center with ES, IS. The second term here, Rs is constant. We keep it out of the integral. Then we have the integral of dm, and the integral of dm is only the mass m. And this terms here, delta Xi dm, it's zero. Why? Because we said, yeah, at the center weight, yeah, here it's the static moment of area about S will be always here zero. Okay. Now the moment of inertia about point A can be defined now by IS plus RS square multiplied by the mass M. And this is what we call here the Steiner's part. That it means that now keep in mind, yeah, and this is the important part, yeah, that's what we will use in practice as also, let's say in reality as far we see it in tutorials, okay. First, we have to calculate the moment of inertia about the center with IS, and if we want to calculate the moment of inertia for any arbitrary point on this body, rigid body, in this case, we apply the Steiner part. Okay? The body, we will know the mass, its mass, let's say, and Rs, yeah, it's only the distance between this arbitrary point and the center weight. Okay? And we will use always this equation, let's say. Yeah. Now we take this example, okay, thin bar, which has the total mass M, has the length L, and cross section, yeah, let's say known, okay. Now what we have, we take uh, the pin joint or the fixed point A, yeah, which allows the rotation, yeah, on about this point A, yeah, of uh, the, the thin bar. We take its centroid S. S, of course, if the thin bar has the length L, yeah, the centroid will be at a distance L over 2. Now, if we want to get the moment of inertia about this point A, we calculate the moment of inertia about S, yeah, and then we add the Steiner part. And the Steiner part, we said, it's only Rs, okay, here, square multiplied by the mass. And now Rs, the distance between the central weight S and this point E, it's only L over 2. Then we have L over 2 square multiplied by the mass M. Okay. Is, as we have seen it in the first example, geometrical example, Is is only the 1 over 12 ml square. Okay. This is, yeah, keep them in mind, yeah, for each case, yeah, disk, rectangular disk or plate or circular disk or cylindrical or rod and so on. Find Is is ml square divided by 12, yeah, and this here geometrical problem, yeah, come to this case here. Okay. Now, if we take the point, the moment of inertia, we replace Is by its value, okay, and we take the Steiner part. And now we see that Ia is 1/3 of mass L square, okay. As you can see it now here, yeah, the moment of inertia, yeah, will be the value will be different, yeah, yeah, you consider it or you calculate it at, yeah, for different point. Okay, for the center weight, it's 1 divided by 12. For the point A here, will be 1 divided by 3. Okay, now we take this circular disc or circular drum. Remember, this is we found for, not this one, for this is the thin, and this is the example what we found, and we found Is at the center weight, it's only the half of the mass multiplied by R square. This is at the center weight, okay? Now, if come to the example, now we have here the total mass M with the length L, constant cross section, okay? The pin joint here in A allows rotation in the plus. The mass moment of inertia about A. We use the sum equation at the central width plus the Steiner part. For the Steiner part, the distance between S, the central width, and the point A is only the radius R. Okay. Now, if we replace, we found Is is only the half of the mass multiplied by R square. Okay. Now, if we make we replace, we find Ia is 3 divided by 2, the mass multiplied by the radius square. Okay. I will stop here for today. Yeah. I know it's a lot of equations, but yeah, when we come to the momentum and so on, yeah, we will need, yeah, for that to calculate the moment, moment of inertia. For the moment of inertia, first we determine it for typical geometry or the considered geometry first at the center width, and after this, yeah, and to come to an arbitrary um, point. Okay, this is will be more clear. Hope, yeah, with the tutorial, yeah, and you will see the methodology. This is will be the same methodology applied only, yeah, for different, let's say, geometry and different problems. You at 4 p.m. yeah for the tutorial, and